Let us now try to find the energy stored in a capacitor. The energy stored in the capacitor. So capacitor is an element. We usually draw this the second one of the plate as a straight line, the other one in this curvy fashion, but uh, this does not really make much of the difference when you are going to solve circuits that you can draw capacitors like two parallel plates to save time, because we have to be careful in drawing this curve. So if you don't have much time, you can draw just two parallel plates. Usually this is basically to show the negative, where the negative polarity of a voltage source, for example, may go. And real practical capacitors are marked with a terminal on them, may be marked with the negative sign. So such capacitors are known as polarized capacitors, and it must be very important that the voltage at this terminal should never go higher than the voltage at this terminal, because in that case they may burn out. So let us try to find how much energy does this capacitor store. Obviously, in a circuit element, we know the energy basically depends on the power supplied to the capacitor, and in a circuit element, power is equal to V into I. And here in this case, it is going to be V into IC dV by dt. So again, we can see that this is equal to V C dV, and we can take this dt to the other side, P dt. Now if we integrate this side with respect to time, and if we integrate this side with respect to V and some earlier time t naught and the current time t, because this t appears in the limit, so we are going to have this variable name changed, and V at t naught and V at t, and this variable name changed as well. So we are going to get the energy. So what is this? The power transferred integrated from t naught to t basically is going to give us the change in the energy from t naught to t, or we are going to get the energy at t minus the energy at t naught. So whatever the energy was at t naught, this is going to change, um, find the change in the energy level. This is equal to, and what do we get here? C is a constant, we get it at the outside, and here we have an integral of x, where x is V actually. So what do we get here when we solve this? We get V dash square by 2, and the limits are Vt naught to Vt, and thus we are going to get 1 by 2 C, and we are going to get Vt square minus Vt naught square. So this is what we get. Energy at T minus energy at T naught is equal to half C V T square. Let me write it this way because of mathematical ambiguity. Minus half C V at T naught square. So suppose the capacitor was initially unenergized. Suppose the capacitor was initially unenergized at T naught. So at T naught, let us suppose the capacitor had zero energy, with, or it was unenergized or not charged. It means that V T naught is zero as well. So what do we get here? The energy at T naught is also zero. So we get the energy at T is equal to half. This is the energy at T naught, because Vt naught is 0, so this is going to be 0 as well. Half C and Vt square. Or if we drop this T just for simplicity, the energy of a capacitor is equal to half CV square. So whatever the current voltage of the capacitor is, that tells how much energy it is holding. So V is the current voltage in volts, and omega is the current amount of energy it holds in joules. So this is a good relationship to know for a capacitor.